In this lesson, we're exploring angle bisectors in triangles. And so in this explore activity, they have you drawing an angle on tracing paper and then using folding to create the angle bisector. I'm using my projector, so I can't show you paper folding on my screen, but I did on the next screen actually construct the angle bisector, so I'm going to use that. So what they're wanting us to do is to use the ruler to draw several different segments from point B to ray BA and measure the length of the segments and measure the angle each segment makes with BA. So here's angle A, B, C. Here is point P, and it's wanting me to measure different distances from P to ray BA. Here's ray BA, and I can measure the distance from P to BA by maybe drawing this segment, or this segment, or this segment. And visually, I hope that you notice this segment is the shortest of the three. Then it's asking to measure the angle formed by the segment drawn and BA. So again, I'm not going to pull out a protractor to do this, but I hope that you would notice that it looks really, really stinking close to 90 degrees. So back here, what do I notice about the shortest segment we can draw from point B to line BA or ray BA? The shortest segment is perpendicular to BA. And shortest segment I can draw from P to BC, measure its length. How does its length compare to the length of the shortest segment I drew from P to BA? Okay, so similar idea. If I draw that perpendicular segment, and again, I'm drawing, I'm not constructing, so my segments aren't perfect, but again, I hope that you notice that these two segments end up being congruent. So suppose I choose a point Q on the bisector of angle XYZ, and I draw the perpendicular segment from Q to YX and the perpendicular segment from Q to YZ. What do I think will be true about these segments? They will be congruent. So what do you think is the best way to measure the distance from a point to a line? Best way to measure the distance from a point to a line is measure the length of the segment from the point that is perpendicular to the line. And so since that perpendicular segment from the point on the angle bisector is the same distance to either side of the angle, what we've ended up saying is that any point on the angle bisector of an angle is equidistant to the sides of the angle. And so we're noticing that property here, that since the distance from a point to a line is the length of the perpendicular segment from the point to the line, I'm going to say pretty much exactly what we just finished saying, that if a point is on the bisector of an angle, then it is equidistant from the sides of the angle. We have the converse of that angle bisector theorem that says if a point in the interior of an angle is equidistant from the sides of the angle, then it is on the bisector of the angle. So in example 1, they're asking to find the length of LM. So I'm given in this diagram, and notice it's not made very big. Notice these arcs that they had there. Those arcs indicate that KM is an angle bisector. So since M is on the angle bisector, it will be equidistant from the sides of the angle. So that's why the length of LM is also 12.8. Similar idea in part B. I notice that AD is equal to CD, and that AD is perpendicular to BA, DC is perpendicular to BC, so that means that BD bisects angle ABC by the converse of the angle bisector theorem. So the measure of angle ABD will be half of the measure of angle ABC, and half of 112 is 56. In this reflect question, it's saying in the converse of the angle bisector theorem, why is it important to say that the point must be in the interior of the angle? Well, the conclusion that we draw in the converse of the angle bisector theorem is that the point lies on the angle bisector. Well, if I have an angle and I have a point on the exterior of the angle, that point isn't going to be on the angle bisector. Okay, so why is it important to say that the point must be in the interior of the angle? Because it lies on the angle bisector. Which is in the interior of the angle. Here we're finding the measure of segment QS. So again, notice the markings. These arc markings indicate that PS is an angle bisector. So since the distance from S to PR is 14, then the distance from S to PQ will also be, 14.7. In the last lesson, we learned that there's a very important relationship between the intersections of the perpendicular bisectors of the sides of a triangle and a very special circle with regards to that triangle. We have a similar relationship here. First, some vocabulary. Notice that a circle is inscribed in a polygon if each side of the polygon is tangent to the circle, and that might not be a term that you're familiar with. Tangent to the circle means that each side of the polygon is just barely touching the circle. And circle C is inscribed in quadrilateral WXYZ, and we say that the circle is the incircle of that quadrilateral. Well, in this lesson, we're talking about the incircle for triangles, and the center of the incircle is the incenter. And they're saying in example 2 to use a compass and straight edge to construct the inscribed circle. So the center of the inscribed circle must be equidistant from segment PQ and segment PR. And what is the set of points equidistant from PQ and PR? It would be the bisector of angle QPR. So I'm going to bisect angle P. Let's remember how to do that. When you're bisecting an angle, you're placing the point of your compass at its vertex, and making an arc on that angle. And then from each of the points at which that arc crosses your angle, we're making another arc in the interior of the angle. Those arcs intersect, so I draw the ray from the vertex of the angle P to the intersection of those arcs. That's a little bit off. Let's see if I can do that a little better. The center must also be equidistant from PR and QR. I'm reading from step 2. What is the set of points equidistant from PR and QR? It would be the bisector of angle R. So I'm going to bisect that angle. Same steps. Those arcs intersect, so from my vertex R to that point of intersection, and again, that wasn't my best work. So that's a little better. Notice where those angle bisectors intersect. They intersect here. That is the center of my in-circle, excuse me. So in step 3, it says the center must lie at the intersection of the two sets of points you constructed. Label this point C. Place the point of your compass at C and open the compass until the pencil just touches a side of triangle PQR. And I'm not drawing it yet. But do you see how it would just barely, and I'm a little bit off. So, there we go. Notice how that circle just barely touches the sides of the triangle. And of course, yes, I'm going to acknowledge that it doesn't touch the side PQ. My construction isn't perfect. And a lot of times, your constructions won't be perfect. But as long as you're showing the steps, as long as you understand the steps, then you're in good shape. Suppose we had started by constructing the set of points equidistant from PR and QR, and then constructed the set of points equidistant from QR and QP. Would we have found the same center point? And it says check this by doing the construction. In the interest of keeping my videos at a reasonable length, I'm not going to do that. But yes, we would have found the same center point. Because angle bisectors of a triangle are concurrent, meaning all 3 of them intersect in one point. As I mentioned earlier, that is the in-center. And so, very much like how in the last lesson, the distance from the circumcenter was always the same to all of its vertices, the distance from the incenter to all of the sides is also congruent. So in this example, I am told that JV and KV are angle bisectors, and I'm asked to find these different measures. I'm asked to find the distance from V to KL, and the distance from V to KL would be the same as the distance from V to JK. Notice that since the distance from V to JK is 7.3, that's why the distance from V to KL is also 7.3. In part B, I'm asked for the measure of angle VKL. That's this angle here. Well, I know that JV is the angle bisector of angle KJL. And that means that the measure of angle KJL will be 2 times 19, so that'll be 38. The triangle sum theorem says that 38 that I just found plus 106, the measure of angle L, plus the JKL that I'm looking for, angle JKL, which is the third angle of the triangle, has to add up to 180. So when I subtract what 38 plus 106 add up to, that's 144. So I'm subtracting 144 from both sides, and I get 36. So KV is the bisector of angle JKL, so that means VKL will be half of 36, which is 18. In part A, is there another distance that we can determine? Well, let's take a closer look. In part A, could I find another distance? Yes, I could find the distance from V to JL. It would also be 7.3. Similar idea in this your turn example. I am given some measurements in this diagram. I'm asked in number 8 for the distance from X to PQ. So I'm told in the instructions that QX and RX are angle bisectors, and since they both have the point X in common, X must be the incenter, which means that the distance from X to each of the sides is all going to be the same. So the distance from X to PR is 19.2. So that means that the distance from X to PQ will also be 19.2. I'm asked for the measure of angle PQX. That's this angle. Again, I know that the measure of this whole thing is 24. I take 24 plus 52, and that's 76. 180 minus 76 is 104, which is the measure of angle PQR. But I was told that PQR got bisected. So, in order to find angle PQY, I take half of 104 to get 52. In this elaborate question, they've told us that P and Q are the circumcenter and incenter of the triangle, but not necessarily in that order. So which point would be the circumcenter and which point would be the incenter? In order for the incenter to be the center of the circumscribed circle, it has to be inside the triangle. So P is the incenter, and Q is the circumcenter. Okay, so we have this table that kind of hopefully helps you keep track of the difference between the circumcenter and the incenter. The circumcenter is the point of concurrency of the perpendicular bisectors, and of course those are of the sides. The incenter is the point of concurrency of the angle bisectors. And I hope that that's kind of self-explanatory, that it's bisecting angles. The circumcenter is equidistant from the vertices, whereas the incenter is equidistant from the sides. The circumcenter can be located in, out, or on. I showed you that in the graphic in the previous video where I clicked and dragged a point of the triangle and you saw the circumcenter go in the triangle when it's acute, you saw it go outside when it's obtuse, you saw it be on when it's a right triangle. Whereas the incenter is always inside the triangle.